Learning objectives. In this chapter, the user would learn the following aspects of processor technology used in embedded system: memory system architecture, input-output subsystem, 16 or 32-bit embedded processor and microcontrollers, processor performance enhancement. Memory system architecture. In a memory read operation, the CPU loads the address onto the address bus. In most cases, these lines are fed to a decoder which selects the proper memory location. The CPU then sends a read control signal. The data stored in that location is transferred to the processor via the data lines. In the memory write operation, after the address is loaded, the CPU sends the write control signal followed by the data to the requested memory location. The memory can be classified in various ways, that is, based on the location, power consumption, way of data storage, etc. The memory at the basic level can be classified as processor memory, register array, internal on-chip memory, primary memory, cache memory, secondary memory. Processor memory. Most processors have some registers associated with arithmetic logic units. They store the operands and the result of an instruction. The data transfer rates are much faster without needing any additional clock cycles. The number of registers varies from processor to processor. The more is the number, the faster the instruction execution. But the complexity of the architecture puts a limit on the amount of the processor memory. Cache memory. This is situated between the processor and the primary memory. This serves as a buffer to the immediate instructions or data which the processor anticipates. There can be more than one level of cache memory. The contents are erased when the power is switched off. Semiconductor random access memories fall into this category. The contents are intact even if the power is switched off. Magnetic memories, hard disks, optical disks, CD-ROMs. Usually designed with SRAM, faster but more expensive than DRAM. Usually on same chip as processor, space limited, so much smaller than off-chip main memory. Faster access, one cycle versus several cycles for main memory. Cache operation. Request for main memory access, read or write. First, check cache for copy. Cache hit. Copy is in cache, quick access. Cache miss. Copy not in cache, read address and possibly its neighbors into cache. Several cache design choices. Cache mapping, replacement policies, and write techniques. Cache mapping is necessary as there are far fewer number of available cache addresses than memory. Are addresses contents in cache? Cache mapping used to assign main memory address to cache address and determine hit or miss. Three basic techniques: direct mapping, fully associative mapping, set associative mapping. Cache are partitioned into individual blocks or lines of adjacent memory addresses, usually 4 or 8 addresses per line. Cache replacement policy. Technique for choosing which block to replace when fully associative cache is full, when set associative cache's line is full. Direct mapped cache has no choice. Random, replace block chosen at random. LRU, least recently used. Replace block not accessed for longest time. FIFO, first in, first out. Push block onto queue when accessed. Choose block to replace by popping queue. Cache write techniques. When written, data cache must update main memory. Write through. Write to main memory whenever cache is written to. Easiest to implement. Processor must wait for slower main memory write. Potential for unnecessary writes. Write back. Main memory only written when dirty block replaced. Extra dirty bit for each block set when cache block written to reduces number of slow main memory writes. Cache impact on system performance. Total size of cache, total number of data bytes cache can hold, tag, valid and other housekeeping bits not included in total. Degree of associativity, data block size. Larger cache achieve lower miss rates but higher access cost. For example, 2 kilobytes of cache, miss rate is equal to 15%, hit cost is equal to 2 cycles, miss cost is equal to 20 cycles. Average cost of memory access is 0.85 into 2 plus 0.15 into 20, which is equal to 4.7 cycles. 4 kilobyte cache, miss rate is equal to 6.5%, hit cost is equal to 3 cycles, miss cost will not change. Average cost of memory access is equal to 0.935 into 3 plus 0.065 into 20, which is equal to 4.105 cycles, which is an improvement. Cache performance trade-offs. Improving cache hit rate without increasing size. Increase line size. Change set associativity. Virtual memory. Improving cache hit rate without increasing size. Increase line size. Change set associativity. Virtual memory is stored in a hard disk image. The physical memory holds a small number of virtual pages in physical page frames. A mapping between a virtual and physical memory. The page table maps between virtual memory and physical memory. Virtual memory was invented to relieve programmers from burdens. VM allows efficient and safe sharing of main memory among multiple programs. Consider a collection of programs running all at once on a computer. We don't want to know which programs will share main memory with other programs when we compile them. In fact, the programs sharing main memory change dynamically while the programs are running. Because of this dynamic interaction, we would like to compile each program into its own address space, virtual address space. VM provides the ability to easily run programs larger than the size of physical memory. In the olden days, if a program was too large for memory, it was the programmer's responsibility to make it fit. Programmers divided programs into pieces and then loaded and unloaded pieces into main memory under users' program control. Virtual memory is a technique provided by operating systems such as Windows and Linux. Virtual memory uses main memory as a cache for secondary storage. Virtual memory automatically manages the two levels of memory hierarchy, main memory and secondary storage. Virtual memory space is split into fixed sized blocks, which are called pages, which are typically 4 KB. Operating systems create page tables that translate virtual address to physical address. The assumption of operating systems developers is that any user program cannot be trusted. User programs will try to destroy themselves, other user programs, and the operating system itself. That seems like such a negative view. However, it's how operating systems are designed. It's not necessary that programs have to be deliberately malicious. Programs can be accidentally malicious, modify the data of a pointer pointing to garbage memory. When a computer is running, many programs are simultaneously sharing the CPU. Each running program plus the data structures need to be managed. It is called a process. Each process is allocated an address space. This is a set of valid addresses that can be used. This address space can be changed dynamically. For example, the program might request additional memory from the dynamic memory allocation from the operating system. If a process tries to access an address that is not part of its address space, an error occurs, and the operating system takes over, usually killing the process, code dumps, etc. In a cache, we fetched quantities called data blocks or cache lines. Those are typically somewhere between, say, 4 and 64 bytes. There is a corresponding terminology in virtual memory to a cache line. It is called a page. A page is a sequence of n bytes where n is a power of 2. These days, page sizes are at least 4K in size and may be as large as 64K or more. Memory Management Unit and Translation. A Memory Management Unit, MMU, sometimes called Paged Memory Management Unit, PMMU, it is a computer hardware unit having all memory references pass through it, primarily performing the translation of virtual memory addresses to physical addresses. It is usually implemented as part of the Central Processing Unit, CPU, but it also can be in the form of a separate integrated circuit. Modern MMUs typically divide the virtual address space, the range of addresses used by the processor, into pages, each having a size which is a power of 2, usually a few kilobytes, but they may be much larger. The bottom bits of the address, the offset within a page, are left unchanged. The upper address bits are the virtual page numbers. In some cases, a page fault may indicate a software bug. A key benefit of an MMU is memory protection. An OS can use it to protect against errant programs by disallowing access to memory that a particular program should not have access to. Typically, an OS assigns each program its own virtual address space. An MMU also mitigates the problem of fragmentation of memory. After blocks of memory have been allocated and freed, the free memory may become fragmented, discontinuous, so that the largest contiguous block of free memory may be much smaller than the total amount. The x86 architecture provided segmentation rather than paging in the 80286 and provides both paging and segmentation in the 80386 and later processors. Most modern systems divide memory into pages that are 4 to 64 KB in size, often with the capability to use huge pages from 2 MB to 512 MB in size. Page translations are cached in a translation look-aside buffer, TLB. Some systems, mainly older RISC designs, trap into the OS when a page translation is not found in the TLB. Most systems use a hardware-based tree walker. Most systems allow the MMU to be disabled, but some disable the MMU when trapping into OS code. VM address translation must be very cheap on average. Every instruction includes 1 or 2 memory references, including the reference to the instruction itself. VM translation is supported in hardware by a Memory Management Unit or MMU. The addressing model is defined by the CPU architecture. The MMU itself is an integral part of the CPU. The role of the OS is to install the virtual physical mapping and intervene if the MMU reports that it cannot complete the translation. The OS controls the operation of the MMU to select, number 1, the subset of possible virtual addresses that are valid for each process, the process virtual address space. 2, the physical translations for those virtual addresses. 3, the modes of permissible access to those virtual addresses, read, write, execute. 4, the specific set of translations in effect at any instant need rapid context switch from one address space to another. MMU completes a reference only if the OS says it's okay. MMU raises an exception if the reference is not okay. An on-chip hardware translation buffer, TB or TLB, caches recently used virtual physical translations. Alpha 21164, 48 entry fully associative TLB. A CPU pipeline stage probes the TLB to complete over 99% of address translations in a single cycle. Like other memory system caches, replacement of TLB entries is simple and controlled by hardware. Example, not last used. If a translation misses in the TLB, the entry must be fetched by accessing the page table in memory. Cost 10 to 500 cycles. The OS kernel carries out its memory management functions by issuing privileged operations on the MMU. Choice 1. OS maintains page tables examined by the MMU. MMU loads TLB autonomously on each TLB miss. Page table format is defined by the architecture. OS loads page table bases and lengths into privileged memory management registers on each context switch. Choice 2. OS controls the TLB directly. MMU raises exception if the needed PTE is not in the TLB. Exception handler loads the missing PTE by reading data structures in memory, software loaded TLB. Input-output subsystem. The traditional definition of input-output is they are devices that create a medium of interaction with the human users. They fall into the following categories such as printers, visual display units, keyboard, cameras, plotters, scanners. However, in real-time embedded systems, the definition of input-output devices is very different. An embedded controller needs to communicate with a wide range of devices, namely analog to digital AD and digital to analog DA converters. Codecs. The functionality of an embedded system can be broadly classified as processing, transformation of data, implemented using processors storage, retention of data, implemented using memory and communication, also called interfacing, transfer of data between processors and memories, implemented using buses. System address bits 19:0 are used to address memory and input-output devices within the system. These signals may be used along with LA23 to LA17 to address up to 16 megabytes of memory. Only the lower 16 bits are used during the input-output operations to address up to 64K input-output locations. SA19 is the most significant bit. SA0 is the least significant bit. These signals are gated on the system bus when BALE is high and are latched on the falling edge of BALE. They remain valid throughout a read or write command. These signals are normally driven by the system microprocessor or DMA controller, but may also be driven by a busmaster on an ISA board that takes ownership of the bus. A microprocessor communicates with other devices using some of its pins. Broadly, we can classify them as port-based input-output, parallel input-output. Processor has one or more n-bit ports. Processor software reads and writes a port just like a register. Bus-based input-output. Processor has address, data, and control ports that form a single bus. Communication protocol is built into the processor. A single instruction carries out the read or write protocol on the bus. Parallel input-output peripheral. When processor only supports bus-based input-output, but parallel input-output is needed, types of bus-based input-output, memory-mapped input-output, and standard input-output. Processor talks to both memory and peripherals using the same bus. Two ways to talk to peripherals. Memory-mapped input-output. Peripheral registers occupy addresses in same address space as memory. For example, bus has 16-bit address. Lower 32K addresses may correspond to memory. Upper 32K addresses may correspond to peripherals. Standard input-output, input-output, mapped input-output. Additional pin M or IO on bus indicates whether it's a memory or a peripheral access. Example, bus has 16-bit address. All 64K addresses correspond to memory. Memory mapped input-output versus standard input-output. Memory mapped input-output requires no special instructions. Assembly instructions involve memory like MOV and ADD, work with peripherals as well. Standard input-output requires special instructions, for example in, out, to move data between peripheral registers and memory. Standard input-output, no loss of memory addresses to peripherals. Simpler address decoding logic in peripherals is possible. When the number of peripherals is much smaller than address space, then high order address bits can be ignored. Smaller and or faster comparators, a basic memory protocol. Input-output subsystem busy wait. Processor speeds vary greatly from computer to computer, especially as some processors are designed to dynamically adjust speed based on external factors such as the load on the operating system. As such, spinning as a time-delayed technique often produces unpredictable or even inconsistent results unless code is implemented to determine how quickly the processor can execute a do-nothing loop. Spinning can be a valid strategy in certain circumstances, most notably in the implementation of spin locks within operating systems designed to run on SMP systems. Most operating systems and threading libraries provide a variety of system calls that will block the process on an event, such as lock acquisition, timer changes, input-output availability, or signals. Using such calls generally produces the simplest, most efficient, fair, and race-free result. A single call checks and informs the scheduler of the event it is waiting for, inserts a memory barrier where applicable, and may perform a requested input-output operation before returning. Other processes can use the CPU while the caller is blocked. The scheduler is given the information needed to implement priority inheritance or other mechanisms to avoid starvation. Input-output subsystem DMA. DMA stands for Direct Memory Access. DMA is a method of transferring data from the computer's RAM to another part of the computer without processing it using the CPU. While most data that is input or output from your computer is processed by the CPU, some data does not require processing or can be processed by another device. In these situations, DMA can save processing time and is a more efficient way to move data from the computer's memory to other devices. The CPU is using programmed input-output. It is typically fully occupied for the entire duration of the read or write operation and is thus unavailable to perform other work. With DMA, the CPU initiates the transfer, does other operations while the transfer is in progress, and receives an interrupt from the DMA controller when the operation is done. This feature is useful anytime the CPU cannot keep up with the rate of data transfer or where the CPU needs to perform useful work while waiting for relatively slow input-output data transfer. Many hardware systems use DMA, including disk drive controllers, graphics cards, network cards, and sound cards. DMA is also used for intra-chip data. DMA can also be used for memory-to-memory copying or moving of data within memory. DMA can offload expensive memory operations such as large copies or scatter-gather operations from the CPU to a dedicated DMA engine. An implementation example is the input-output acceleration technology. A DMA controller can generate memory addresses and initiate memory read or write cycles. It contains several processor registers that can be written and read by the CPU. Modes of operation. An entire block of data is transferred in one contiguous sequence. Once the DMA controller is granted access to the system bus by the CPU, it transfers all bytes of data in the data block before releasing control of the system buses back to the CPU, but renders the CPU inactive for relatively long periods of time. The mode is also called block transfer mode. It is also used to stop unnecessary data. The cycle stealing mode is used in systems in which the CPU should not be disabled for the length of time needed for burst transfer modes. Input-output subsystem, interrupt-driven input-output. The problem with programmed input-output is that the processor has to wait a long time for the input-output module of concern to be ready for either reception or transmission of data. The processor, while waiting, must repeatedly interrogate the status of the input-output module. This type of input-output operation, where the CPU constantly tests a part to see if data is available, is polling. That is, the CPU polls or asks the port if it has data available or if it is capable of accepting data. Polled input-output is inherently inefficient. For input, the input-output module services a read command from the processor. The input-output module then proceeds to read data from an associated peripheral device. Once the data are in the module's data register, the module issues an interrupt to the processor over a control line. The module then waits until its data are requested by the processor. When the request is made, the module places its data on the data bus and is then ready for another input-output operation. The processor issues a read command. It then does something else. For example, the processor may be working on several different programs at the same time. At the end of each instruction cycle, the processor checks for interrupts. When the interrupt from an input-output module occurs, the processor saves the context, for example, program counter and processor registers of the current program, and processes the interrupt. In this case, the processor reads the word of data from the input-output module and stores it in memory. It then restores the context of the program it was working on and resumes execution. The device issues an interrupt signal to the processor. The processor finishes execution of the current instruction before responding to the interrupt. The processor tests for the interrupt. If there is one interrupt pending, and then the processor sends as acknowledgement a signal to the device which issued the interrupt. After getting acknowledgement, the device removes its interrupt signals. The processor now needs to prepare to transfer control to the interrupt routine. It needs to save the information needed to resume the current program at the point of interrupt. The minimum information required to save is the processor status word PSW and the location of the next instruction to be executed, which is nothing but the contents of program counter. Two design issues arise in implementing interrupt input-output. There will almost invariably be multiple input-output modules. How does the processor determine which device issued the interrupt? If multiple interrupts have occurred, how the processor does decide which one to process? Multiple interrupt lines. The most straightforward approach is to provide multiple interrupt lines between the processor and the input-output modules. It is impractical to dedicate more than a few bus lines or processor pins to interrupt lines. Thus, throughout multiple interrupt lines are needed, it is most likely that each line will have multiple input-output modules attached to it. Thus, one of the other three techniques must be used on each line. Software poll. When the processor detects an interrupt, it branches to an interrupt service routine whose job is to poll each input-output module to determine which module caused the interrupt. There are several techniques to identify the requesting input-output module. These techniques also provide a way of assigning priorities when more than one device is requesting interrupt service. With software polling, the order in which modules are polled determines their priority. In case of daisy chain configuration, the priority of a module is determined by the position of the module in the daisy chain. The module nearer to the processor in the chain has got higher priorities because this is the first module to receive the acknowledge signal that is generated by the processor. 16 or 32-bit embedded processor and microcontrollers. In the 1950s, IBM instituted a research program. In 1964, release of System 360. In the mid-1970s, improved measurement tools demonstrated on CISC. In 1975, 801 project initiated by IBM's Watson Research Center. In 1979, 32-bit RISC microprocessor 801 developed by Joel Binbaum. In 1984, MIPs developed at Stanford as well as projects done at Berkeley. In 1988, RISC processors had taken over high end of the workstation market. In the early 1990s, IBM's PAR, Performance Optimization with Enhanced RISC, architecture introduced with the RISC system 6K. AIM, Apple, IBM, Motorola alliance formed, resulting in PowerPC. CISC is an acronym for Complex Instruction Set Computer and are chips that are easy to program and make efficient use of memory. Since the earliest machines were programmed in assembly language and memory was slow and expensive, the CISC philosophy made sense and was commonly implemented in such large computers as the PDP-11 and the DEC System 10 and 20 machines. Most common microprocessor designs, such as the Intel 80x86 and Motorola 68K series, followed the CISC philosophy. But recent changes in software and hardware technology forced a re-examination of CISC, and many modern CISC processors are hybrids implementing many RISC principles. CISC was developed to make compiler development simpler. It shifts most of the burden of generating machine instructions to the processor. For example, instead of having to make a compiler write long machine instructions to calculate a square root, a CISC processor would have a built-in ability to do this. The design constraints that led to the development of CISC, small amounts of slow memory, and fact that most early machines were programmed in assembly language give CISC instruction sets some common characteristics. A two-operand format, where instructions have a source and a destination, register to register, register to memory, and memory to register commands. Multiple addressing modes for memory, including specialized modes for indexing through arrays. Variable length instructions, where the length often varies according to the addressing mode. Instructions which require multiple clock cycles to execute. For example, Pentium is considered a modern CISC processor. Most CISC hardware architectures have several characteristics in common. Complex instruction decoding logic driven by the need for a single instruction to support multiple addressing modes. A small number of general purpose registers. This is the direct result of having instructions which can operate directly on memory and the limited amount of chip space not dedicated to instruction decoding, execution, and microcode storage. Several special purposes register. Many CTSC designs set aside special registers for the stack pointer, interrupt handling, and so on. This can simplify the hardware design to a certain extent, at the expense of making the instruction set more complex. A condition code register, which is set as a side effect of most instructions. This register reflects whether the result of the last operation is less than, equal to, or greater than 0 and records if certain error conditions occur. At the time of their initial development, CISC machines used available technologies to optimize computer performance. Microprogramming is as easy as assembly language to implement and much less expensive than hardwiring a control unit. The ease of microcoding new instructions allowed designers to make CISC machines upwardly compatible. A new computer could run the same programs as earlier computers because the new computer would contain a superset of the instructions of the earlier computers. As each instruction became more capable, fewer instructions could be used to implement a given task. This made more efficient use of the relatively slow main memory. Because microprogram instruction sets can be written to match the constructs of high-level languages, the compiler does not have to be as complicated. Designers soon realized that the CISC philosophy had its own problems, including earlier generations of a processor family generally were contained as a subset in every new version. So instruction set and chip hardware became more complex with each generation of computers. So that as many instructions as possible could be stored in memory with the least possible wasted space, individual instructions could be of almost any length. This means that different instructions will take different amounts of clock time to execute, slowing down the overall performance of the machine. Many specialized instructions aren't used frequently enough to justify their existence. Approximately 20% of the available instructions are used in a typical program. CISC instructions typically set the condition codes as a side effect of the instruction. Not only does setting the condition codes take time, but programmers have to remember to examine the condition code bits before a subsequent instruction changes them. RISC, or Reduced Instruction Set Computer, is a type of microprocessor architecture that utilizes a small, highly optimized set of instructions rather than a more specialized set of instructions often found in other types of architectures. History. The first RISC projects came from IBM, Stanford, and University of California at Berkeley in the late 1970s and early 1980s. The IBM 801, Standard MIPS, and Berkeley RISC 1 and 2 were all designed with a similar philosophy which has become known as RISC. Certain design features have been characteristic of most RISC processors. The main characteristics of CISC microprocessors are extensive instructions, complex and efficient machine instructions, micro encoding of the machine instructions, extensive addressing capabilities for memory operations, relatively few registers. In comparison, RISC processors are more or less the opposite of the above. Reduced instruction set, less complex, simple instructions, hardwired control unit, and machine instructions. Few addressing schemes for memory operands with only two basic instructions, load and store. There is still considerable controversy among experts about the ultimate value of RISC architectures. Its proponents argue that RISC machines are both cheaper and faster and are therefore the machines of the future. However, by making the hardware simpler, RISC architectures put a greater burden on the software. Is this worth the trouble? Because conventional microprocessors are becoming increasingly fast and cheap anyway. CISC and RISC convergence. State-of-the-art processor technology has changed significantly since RISC chips were first introduced in the early 1980s. Because a number of advancements are used by both RISC and CISC processors, the lines between the two architectures have begun to blur. In fact, the two architectures almost seem to have adopted the strategies of the other. Because processor speeds have increased, CISC chips are now able to execute more than one instruction within a single clock. This also allows CISC chips to make use of pipelining. With other technological improvements, it is now possible to fit many more transistors onto a single chip. DSP processors. A digital signal processor is a specialized microprocessor or a SIP block with its architecture optimized for the operational needs of digital signal processing. Most general-purpose microprocessors can also execute digital signal processing algorithms successfully, but dedicated DSPs usually have better power efficiency, thus they are more suitable in portable devices such as mobile phones because of power consumption constraints. DSPs often use special memory architectures that are able to fetch multiple data and/or instructions at the same time. Digital signal processing algorithms typically require a large number of mathematical operations to be performed quickly and repeatedly on a series of data samples. Signals, perhaps from audio or video sensors, are constantly converted from analog to digital, manipulated digitally, and then converted back to analog form. Many DSP applications have constraints on latency. That is, for the system to work, the DSP operation must be completed within some fixed time, and deferred or batch processing is not viable. The standards of general purpose processors, DSP instruction sets, are often highly irregular. One implication for software architecture is that hand-optimized assembly code routines are commonly packaged into libraries for reuse instead of relying on advanced compiler technologies to handle essential algorithms. Hardware features visible through DSP instruction sets commonly include hardware module addressing, allowing circular buffers to be implemented without having to constantly test for wrapping. Memory architecture designed for streaming data using DMA extensively and expecting code to be written to know about cache hierarchies and the associated delays. Driving multiple arithmetic units may require memory architectures to support several accesses per instruction cycle, separate program and data memories, Harvard architecture, and sometimes concurrent access on multiple data buses. Special SIMD, single instruction multiple data operations. Some processors use VLIW techniques, each instruction drives multiple arithmetic units in parallel. Special arithmetic operations such as fast multiply accumulates MACs. Many fundamental DSP algorithms such as FIR filters or the fast Fourier transform FFT depend heavily on multiply accumulate performance. Bit reversed addressing, a special addressing mode useful for calculating FFTs. Special loop controls such as architectural support for executing a few instruction words in a very tight loop without overhead for instruction fetches or exit testing. Floating point integrated directly into the data path. Pipelined architecture. Highly parallel multiplier accumulators, MAC units. Hardware controlled looping to reduce or eliminate the overhead required for looping operations. DSPs often use special memory architectures that are able to fetch multiple data and or instructions at the same time. Harvard architecture, modified von Neumann architecture, use of direct memory access, memory address calculation unit, saturation arithmetic, in which operations that produce overflows will accumulate at the maximum or minimum values that the register can hold, rather than wrapping around maximum plus 1 doesn't overflow to minimum as in many general purpose CPUs. Instead, it stays at the maximum. Sometimes various sticky bits operation modes are available. Fixed point arithmetic is often used to speed up arithmetic processing. Single cycle operations to increase the benefit of pipelining. Multiple accumulate, MAC, including fused multiply, add FMA operations, which are used extensively in all kinds of matrix operations such as convolution for filtering, dot product, or even polynomial evaluation, see Horner scheme. Instructions to increase parallelism, SIMD, VLIW, superscalar architecture. Specialized instructions for modulo addressing in ring buffers and bit reversed addressing mode for FFT cross-referencing. Digital signal processors sometimes use time stationary encoding to simplify hardware and increase coding efficiency. Modern signal processors yield greater performance. This is due in part to both technological and architectural advancements like lower design rules, fast access to level cache, eDMA circuitry, and a wider bus system. Not all DSPs provide the same speed, and many kinds of signal processors exist, each one of them being better suited for a specific task, ranging in price from about US $1.50 to US $300. Processor performance enhancement. Multi-cycle implementation breaks the major task of each instruction into a series of smaller tasks. Each task in execution will take one clock cycle, which allows functional unit to be used more than once per instruction as long as it is used as different clock cycles. Sharing resources reduce the amount of hardware required. Instructions are allowed to take different number of clock cycles. They can reuse functional units such as memory and ALU registers needed to store values between cycles. Finite state machine to control, because the values of the control signals now depend on which step we are performing. Single memory unit for both instruction and data replaced instant memory and data memory. Single ALU replaced ALU and 2 adder. One or more registers are added after every major functional unit to hold the output of that unit until the value is used in a subsequent clock cycle. Shared memory. Single ALU. Shared units need additional widening MUXS. New temp register to hold data between clock cycles. A, B, ALU out. Instant register memory. Data register. Memory. General purpose registers. Stack. Accumulator. Special purpose registers. PC. CCR. Top of stack register. Return address register. Loop count register alignment, byte, half word, word, double word, addressing modes, register, immediate, displacement, register indirect, indexed, direct or absolute, memory indirect. Motivation, increase throughput with little increase in hardware. Bandwidth or throughput is equal to performance. Bandwidth is equal to number of tasks per unit time. For a system that operates on one task at a time, bandwidth is equal to 1 by latency. Bandwidth can be increased by pipelining if many operands exist which need the same operation. That is, many repetitions of the same task are to be performed. Latency required for each task remains the same or may even increase slightly. Break instructions into smaller pieces of execution, devote hardware to each piece, add flip-flops between stages so that each stage can work independently, modify control hardware to fetch a new instruction every cycle. So, how much does this improvement cost? Is there a limit to how much it can improve performance? Pipeline can be divided into exactly even segments of latency. Example, 700 ns of work, 7 pipeline stages, the ideal case. Work divisible into 7 stages of exactly 100 ns per stage. Pipeline delay is predictable. On each clock cycle, each stage has roughly the same delay. Generally means that each stage does roughly the same thing each time. Like an automobile plant, the paint room paints the car every time. Each stage is independent specifically. Each stage is not waiting on some other stage to do something. Conclusion. In this chapter, the user has covered the following aspects of processor technology used in embedded systems: memory system architecture, input-output subsystem, 16 or 32-bit embedded processor and microcontrollers, processor performance enhancement.